Last episode, we shipped our model the heavyweight way, saved model TensorFlow serving TensorFlow JS. We gave it a server, an endpoint, a URL. But here's the thing, a phone in your pocket doesn't have a server, a doorbell camera doesn't. A $5 microcontroller buried in a sensor definitely doesn't. They're offline, they're tiny, and they still need to run our model. So today, the deploy stop on our pipeline takes a hard turn. Off the cloud onto the device. This is TensorFlow Lite and its secret weapon, quantization. Remember what serving needed. A machine that's always on, always reachable, answering requests over the network. That's perfect for a backend. It's useless on an airplane, in a tunnel, or on a battery-powered gadget that has to last a year. The moment the network goes away, a server-based model goes silent. So the edge branch of deploy flips every assumption. The model has to be small enough to fit in a few megabytes of flash, fast enough to answer in milliseconds on a weak chip, and able to run completely offline. No round trip, no latency, no privacy leak. Your data never leaves the device. TensorFlow Lite is how we get there. The converter takes our trained Keras model and rewrites its computation graph into a compact format built for mobile runtimes. It fuses operations, strips away the training-only machinery, and emits a single flat .dflight file, one portable artifact you can drop into an Android app, an iOS app, or firmware. But the file's still kind of big because every weight is a 32-bit float. Quantization asks a sharp question. Do we really need all that precision? What if we stored each weight as an 8-bit integer instead? 4 times fewer bits per number. And the payoff is dramatic. Int8 weights make the model about 4 times smaller on disk and on phone and microcontroller chips, the ones with dedicated integer units. Integer math runs 2 to 3 times faster than floating point. The cost? Accuracy barely moves. We're talking tenths of a percent. You shrink the model by 75% and lose almost nothing. There's one catch, and it's the clever part. To map floats down to integers, TF Lite needs to know the realistic range of numbers flowing through every layer, the min and the max. So we hand it a representative dataset, a small unlabeled sample of real inputs. The converter runs them through, watches the activations, and calibrates the int8 scale for each tensor. 100 or so examples is plenty. Once we have the .flight file, we don't call model.predict anymore. There's no Keras on the device. Instead, we use the interpreter API and it's beautifully bare metal. You allocate the tensors, you copy your input into the input tensor, you invoke, and you read the output tensor back. 4 calls. That's the entire on-device inference loop, and it's identical whether you're on a flagship phone or a microcontroller. Which is the whole magic. It's the same model we trained now running on a phone, a Raspberry Pi or a $5 chip in a sensor, no server in sight. One model deployed everywhere. And that brings our whole pipeline full circle, which is exactly where we go next. Let's look at the code. Here's 27 TF Lite PY. The plan is 4 moves. Load a model we already trained, convert it to a plain float TF Lite, and measure it, convert it again with int8 quantization and a representative dataset, then run both with the interpreter and compare size, accuracy, and speed. 3 short pages, let's take them in order. Page 1. We import TensorFlow, NumPy, time, and OS, then load MNIST and normalize it to the 0 to 1 range, exactly the pre-processing the model was trained with. Then instead of building and training here, we just load the Keras model we saved back when we first built this CNN. It's a deliberately chunky CNN. A fat, dense head pushes it to about 2.3 million weights, which is why its float file lands around 9 megabytes. It's already trained to 98.5%. We're at the deploy stage. Training is behind us. Next, the simplest possible conversion. We create a converter from the Keras model from Keras model, call convert, and write the bytes to MNIST float TF Lite. No optimizations yet. This is the HonestFlow 32 baseline, so we can see exactly what quantization buys us. We grab the file size right after writing it and print a confirmation. Now the representative dataset, the calibration step. This little generator yields 100 real training images, each shaped as a single element batch and cast to float 32. The converter will push these through the graph to learn the activation ranges. Notice it yields a list with one array. That's the signature TF Lite expects, one entry per model input. Here's the NT8 conversion itself. Same starting point, a fresh converter from the Keras model. But now we turn on optimizations with Optimize. Default, hand it our representative dataset, and then lock it down. We force the supported ops to the integer only set and set both the input and output types to int8. That last part matters for true microcontroller deployment. The whole pipeline, in and out, is integers. We convert rightnist int8.tflite and measure it. Page 2. Time to actually run these files the way a device would. This run tflite helper takes a model path and our test images. It builds a tf.lite interpreter, calls allocate tensors and reads the input and output detail dictionaries. Those tell us the tensor indices, shapes and d-types. If the model expects NT8 input, we quantize each image using the scale and 0 point, the converter baked in. That's the input details quantization parameters. Clip it to the NT8 range so nothing wraps around, and feed it integers in exactly the range it calibrated for. Then the inference loop, one image at a time. For each sample, we set tensor on the input index, invoke, and get tensor on the output index, taking the argmax as the predicted digit. We time the whole batch and divide to get average latency per image in milliseconds, then print a one-line progress note. Same for-call rhythm for both models. The only difference is the nt8 path moves integers instead of floats. Page 3 ties it together. We run the float model and the int8 model, compare each set of predictions against the true labels for accuracy, read back the two file sizes in megabytes, and print one clean summary line. Then a quick matplotlib bar chart, file size and latency side by side before and after. The bars for int8 are a fraction of the height, and the accuracy line across the top barely flinches. We save it and print where it went. And there it is, 9 megabytes down to 2.5, 12 milliseconds down to 4, accuracy holding at 98%. The exact same brain that needed a server in the last episode now runs offline, on a chip you could lose in a couch cushion. We've taken our model all the way from a Keras blueprint to something that lives in the real world. Next episode, we close the loop. We walk one complete project end to end, from collecting raw data all the way to a live prediction. Every stage of the pipeline in a single run, the whole journey start to finish.